Hi, welcome to today's webinar, Specifying Systems Using SysML in Core. My name is Eva Dace and I'm a member of the Marketing Department here at Vitech. I will be your host during today's webinar, which is being presented by Warren B. Smith. Warren is a Senior Account Executive at Vitech Corporation. With over 25 years of systems engineering experience, he's worked in many facets of the field, including leading systems engineering teams, teaching early versions of SysML for university extension programs, working for tool vendors, and even starting and operating his own MBSE company. He's worked in both the functional and object-oriented domains and has working expertise with a wide variety of systems including spacecraft, military vehicles, munitions, automotive, helicopter training systems, medical devices, and IT. But of all the systems he's worked on, Warren says that working with amusement park rides was the most fun. Now, before we get started, I need to review a few housekeeping matters. Please take a few moments to get comfortable with your webinar control panel, as this is how you will be able to submit your questions during the presentation. We will address these questions at the end of the webinar, so please stay tuned. Next, I'd like to answer our most asked question. The webinar is being recorded today. You will be able to find the recording in the webinar archive in the resources section of our website within 24 hours of the live presentation. Now I'm going to chat out the link to this archive now so you can have it on hand. All right, there it is. So now let me hand it over to our presenter. Welcome, Warren. It's great to have you with us.
Thanks, Eva. It's great to be here. I'm really excited to be offering this webinar today. There have been quite a few questions about core and SysML, and so today I wanted to go through for the next hour or so and show people how core does support SysML and how it also supports MBSE. So the first question that I often get when I'm talking about this is, what is the difference between MBSE or model-based systems engineering and SysML? People often conflate the two. Here at Vitech, we have a very specific understanding of the differences and the values of each. So I thought that I might just start for a couple of minutes with that. Then I'm going to move into an overview of some of the SysML diagrams, and then I'm going to give you a tool demonstration of core working entirely within the SysML domain. So in systems engineering, there are actually four primary domains of systems engineering. We call them the core four. That's the requirements and behavior domain, where we capture the text in text usually what the system must do in the requirements, and then a list of the behaviors that implement those requirements in the behavior domain. All of that is allocated to architecture. So each piece of the architecture, hardware, software, process, humans, and so forth, all collaborate to perform the behaviors that the system has to perform. And then, of course, we verify and validate all that information. These four domains are also enhanced with ancillary domains that systems engineers are responsible for, like risk analysis and programmatics and many others. We'll be listing those later. Now, when we take systems engineering, which has been performed for decades and decades, and we turn it into model-based systems engineering, what we do is we take the work that the systems engineers must perform and we populate a central repository with that. The central repository, the model, supports all of the different domains, but allows that information to be related. It allows different views of the system to be published, and so on and so forth. So in our view, the value of model-based systems engineering is that people can work collaboratively together. You can leverage your system designs across projects for reuse. You can publish documentation directly out of the model without having to go through manual steps, and a plethora of other values that come out of the model. Diagnostics, it will help find design omissions. And we have an entire webinar that we published at the beginning of the month that you can go view and see what those values are. But when we switch over to MBSE using SysML, Well, what's really changing isn't the fact that we have an underlying model. What's changing is the notation that's used to describe the system. So SysML has a very rich notation for describing requirements, behavior, architecture, and some other aspects of the system design. But that's what SysML is in our view, is it's a very important, widely used notational structure. And so as we look at today's webinar, I'm going to show you how you can build a system using SysML modeling techniques or diagramming techniques over on top of an underlying systems engineering model. So if any of you did see that last webinar, this is the only chart you're going to get from it, but I did want to highlight what the 4 key characteristics are of model-based system engineering. The first is that MBSE is model-centric and not diagram-centric. So instead of making diagrams and having those be the centerpiece of our work product, instead, when we create the diagrams or any other artifacts that we make, we're actually populating an underlying model, and that underlying model becomes the primary work product. From the model, we can generate anything that we need, including a set of diagrams, textual documents, and so forth. This also means that when we're model-centric instead of diagram-centric, people don't have to share diagrams around. They can always access the latest information from a shared common repository, which means there's always what we call one version of the truth. Now, the second characteristic of MBSE is that it has unambiguous notation. The analogy that I use is doctors have complex jobs, and they have lots of unique words to describe all the various parts of the body. When you're going into a surgery, say if you have a badly broken bone, the doctors can go and they can be very specific in how they describe what's going to happen. You know, we're going to mend the femur to this other specific bone. They don't say, you know, we're gonna knit these things together very generally. They're very specific, and by being specific in systems engineering, what it allows us to do is to identify exactly what elements of our system design have been performed. And the value of that is that unambiguous notation is just like this picture shows. The tool, the model, can show us where there are design omissions. It can show us where there are gaps. Just as there's a gap in the jigsaw puzzle, the model can easily find those gaps if we use unambiguous notation. And I'll show you what that means when we combine that with SysML in a few minutes here. The third characteristic of MBSE is that views are generated from the model. So yes, we will create a model today using only SysML notation. But if you wanted to view the outputs in more traditional notations such as n-squared charts or functional flows, you could do that. You can publish views that represent specifications or architecture frameworks like the DoD architecture framework and so forth. So it's very powerful. You can go in one format and come out in another. Finally, the last characteristic of MBSE is that you have MBSE if you have a development system that you can guarantee that you have complete queryable system, and you can run virtual system prototypes. You can simulate your system before you actually start building it using the model. So being able to have a virtual prototype of the system is a very critical aspect of MBSE. So that's what we think of as MBSE. And feel free to go to our webinar archive and pull up this webinar and see it for a whole hour. Now, let's talk about SML, the Systems Modeling Language. I'm going to have a few slides here that offer some kind of lightweight introduction to some of the representations. If you take our MBSE Essentials class, you'll actually get a lot of detail into all of these that we teach. Now, first notable reference. The SysML specification is published by the Object Modeling Group, and you can access it here. It's at version 1.3, and it's a PDF file. It's actually a fairly straightforward read. Now, inside of SysML, the key diagram types fall into several categories. So I've identified those categories. These are my definitions of the categories. They're diagrams. So we have, when we're specifying a system, we have the requirements diagram, the use case diagram, and the parametric diagram. The parametric diagram, an argument could be made that that should go into behavior. I chose to put it here for today's purposes. But essentially, what these diagrams do is give you a representation to capture requirements, data, system requirements, subsystem, and the relationship between those requirements. It gives you a notation for capturing how a system will be used by the users of the system, and then a representation of how various parameters that impact and are important to the system relate to each other and where they're used in the system, in the system itself. The behavior modeling has three specific types of diagrams: activity diagrams, sequence diagrams, and state transition models. The activity diagrams represent a left to right type of representation of threads, time sequenced information through the system. I'll be showing you one of those today, a couple of them. Sequence diagrams highlight the interaction between tasks and activities that occur within the system. It has a time sequencing as well that goes down. Activity diagrams can also show interactions between elements. Finally, the state transition model, which is used in both software and systems engineering, is used to identify the behaviors that occur when the system is in various states. It defines those states and then aggregates the capabilities that occur when the system is dwelling within any given state. Finally, in the architecture area, we have block definition diagrams that come in a variety of flavors, structure and class type diagrams. We also have internal block diagrams, which we use for interface definition, that kind of thing. So I'm going to spend a few minutes here going through each of these diagram types, so people who maybe aren't familiar with them will get an introduction to them before you see them used in core. But one of the things that you'll notice is that systems engineering, this is not systems engineering modeling language, this is systems modeling language. Systems engineers have more responsibility than just this, as rich and deep as this is. Systems engineers have to do these other things. They have to do SysML, and they have to perform and manage risk. They have to perform diagnostics on the design, and make sure that the design is complete. They have to support testing. There's programmatic aspects of systems engineering. What's the programmatic impact of architectural changes? For instance, there's metrics, traceability, docgen, reuse, and of course interface specification. Now there may be some overlap on some of these, but for the most part, these are specific tasks that systems engineers must perform that are done in conjunction with, but alongside or outside of the SysML modeling domain. So from a systems engineering tool perspective, or an MBSE tool perspective, model-based systems engineering tool perspective, we want to be able to support SysML and these other things. So I'm going to go through for a few minutes here some diagram types, and we'll start just on some slides, and then we'll go into the demo in a few minutes. So we'll start with the user and system specification domain. The first type of diagram is called requirements diagram. And this one is shown hierarchically left to right. It's often shown top to bottom. Whether you like it left to right or top to bottom is up to you. But what it shows is the relationship between a set of textual requirements that have been developed that describe the capabilities that a system must have. It's a graphical format to help visualize the structure better. And usually we would use this with a smaller set of requirements. If we had a very large set of requirements, we would use more of a document format or a tabular format in order to represent page after page after page of technical requirements, which some of you have and some of you do not. I will go back. There are a series of stereotypes, which I guess I must have hidden out of this. You can't read these, but these little labels indicate whether a requirement is derived and so forth. There's also stereotypes for architectural elements which satisfy these requirements. So let me move on to use case diagrams now. So use cases are a description of how the user will interact with the system. They were developed back in the 90s by a gentleman named Ivar Jakobsen. He is from the North Country in Europe. I guess that starts with a J, Jakobsen. At any rate, he came up with this stick figure and oval notation to really concentrate people's minds on how the users of the system will interact with the system. So all the stuff that the system does is subsumed and abstracted into these ovals. So it's a very powerful, very powerful diagram for representing that type of view of the system. Now, an actor can be a person, like these stick figures, but an actor can also be another system that might have to interact. And usually in our highly connected world, we have a lot of systems that we interact with whenever we build something new. Just think GPS, right? You want to use GPS, well, you're an actor on their system, or vice versa. There's also textual component to the use case, so that's represented with a description. And you can see here there's a primary and exception flows. Sometimes it's called sunny day scenario and rainy day scenarios. It also identifies the preconditions and post conditions. In other words, what state the system must be in before the use case is valid, and what state the system would be in after the use case is complete, which would be the pre and post conditions. These tend to be suitable for most audiences. And then you can see there's some notation here which I'll be going over. So I've mentioned the actors here. These usually represent people or systems. And then the extension points that we have, these dashed lines, can be includes or extends. Include lets us pull out common system behavior that might be reused over and over again in various use cases. I'll be showing you an example of that in the demo. And then extend represents exceptional behavior, unintended or not planned behavior, but one that the system is designed to accommodate. Finally, use cases can be generalized, so you can have a sub-use case inherit capabilities, preconditions, postconditions, so forth from a super use case and have their own relationships and so forth associated with that. Parametric diagrams. The parametric diagrams inside of SysML are used to represent various technical, numerical, typically datum that relate to specifying performance. You can see that parametrics might involve computations. So you might get a length and a width, and then there might be a block that would calculate an area, that kind of thing, and pass that along. The parametrics are important because they may be sourced by requirement, but then you might want to test the system to make sure that the system has the, say, the intended area that you want, or whatever the parameter is. So the requirements would specify the parameters, the tests would validate or verify them. So moving on from the requirements domain, the specification domain, to the behavior domain, we have these three diagrams that are really key. The first is an activity diagram. The activity diagram is a very useful systems engineering SysML diagram. Why? It's because people can relate to it. It flows from left to right. It can show a lot of richness, which I'll show you in a minute. And so it's very well suited with dealing with general audiences. The other thing that's key about this activity diagram is that it's temporal. It shows sequence of operation. So what happens over here happens before this task or function occurs. And as you can see, you can have a lot of different types of logical behavior. You can have ands and ors, you can have decisions and loops, you can fork and join different flows, you can have data that flows between processes. So these elements here with a little bar at the bottom represent processes. They've been assigned to system architectural components, that's what these mean. But then these items here, like food in this case, represents basically a data item, something that you would find in a data dictionary that flows between those two processes. And the thing that's nice about activity diagrams is that they can represent both system behavior and process behavior. So at Vitech we use activity diagrams often to model production processes, other types of processes, and simulate actually from these diagrams how long it will take to produce, do a production run, or do other operational type concepts. Now we have, there's the concept of swim lanes. Swim lanes represent bands in the SysML world where certain behavior is grouped. Here we have bands that represent the customer, service area, and so forth. And in our case here, these bands or the swim lanes are going from left to right. You can organize the swim lanes in core in a variety of different ways. They don't have to be just columns that represent the architectural elements. They can be, but the richness of being able to do architecture here or along this line gives you lots of flexibility. And in core, our swim lanes do go from left to right, except for sequence diagrams. So talking about sequence diagrams, this has a lot of similarity to the activity diagram, but the lifelines here, time goes down, not left to right, so the lifelines here do represent, in fact, system architectural components. And the processes, activities, or functions that are allocated and assigned to these components are shown temporally from the top going down. The thing that people like about sequence diagrams is that it really does highlight the interactions between systems and the processes that execute those systems, the processes that execute those interfaces. My experience over many years is that more software-oriented engineers are used to and understand this format than general audience. So when I'm talking to a customer, often I'll be using an activity diagram. When I'm talking with a software engineer, I'll often use a sequence diagram. There are blocks and lifelines associated with sequence diagrams. There are information transfers, events that occur between these two architectural elements. Again, I mentioned time goes down. You can capture in the notation. You see this is a parallel. You can have parallel exclusive alternate and loops as well. And you can see down here that I identify the chapters in the SysML book. SysML, I'm sorry, specification. The state transition model is used to aggregate or collect the capabilities that exist when a system is in a certain state. I have a car with a backup sensor and a backup camera. It's a function of the car that I own, but the only way I can access the backup camera is if I have put the car in reverse. In other words, when I transition from park into a state, one of these states might be reverse, then the capability to see what's behind me using the backup camera is available to the user. State transition models are very powerful tools for identifying the various states that the system can operate in, and what capabilities are available when you're in that state. And they're broken up into entry, exit, and do activities, so you can have a series of behaviors that happen when you enter a state, when the system enters a state, or when it enters a state, or when it's just simply dwelling within the state. Transitions, state transitions are also interesting in SysML. They represent the period of time between that the system is in when it's moving from one state prior to a subsequent state. The transitions are triggered from either messages or operations, certain conditions, like when something is complete and the system may transition to another state, or based upon time. I transition from a sleep state to a waking state, if I were a system, at a certain time every day when my alarm goes off at 10 till 6 in the morning. So that's an example of a transition changing the state of me. These are hierarchical, so you can decompose the states, and states can be assigned to various components in the system. Now, the last type of diagram I'm going to talk about is the architectural diagram that we'll move into the demo. There are block definition diagrams identified inside of the SysML spec. They represent basically very classical type hierarchical structures. The has-parts relationship, if you will, is an example of that. You know, a car is composed of a chassis and an engine. An engine is composed of a carburetor and pistons, et cetera, no one has carburetors anymore, but you get the idea. Very, very powerful yet simple structure. SysML also supports the idea of inheritance. SysML is an extension of UML, the Unified Modeling Language, which is a software language, and software like C++, rather, C#, Objective-C. They are object-oriented software languages that support inheritance. Therefore, SysML also supports inheritance with operations and receptions and values. The internal block diagram is a SysML model that shows connectivity and interface between static hierarchical components and what type of information flows across those interfaces. So in SysML, you can represent both, in your architecture, you can represent both the physical elements of your architecture plus the interface elements, which is what you need. So I'm going to move to the demonstration. We'll probably have about 20 minutes of demonstration in core, how you can use these elements and pull them together inside of a core model. And I'm also going to be showing you SysML, and the ones that are in blue are the diagrams I'm going to really dwell on. I might touch on these other ones, but I'll spend the most of the time on the diagrams that are highlighted in the time that we have left. But again, MBSE and core is more than SysML. It is SysML, but it's SysML and these other things. So today I'm going to talk about some design diagnostics. Remember the chart I showed you earlier with the jigsaw puzzle with the piece missing? Well, I'm going to show you that. I'm going to show you how Core can show you the missing pieces, and so you can fill them. I'm going to show you some traceability, some document generation. We're going to have we plan on having another SysML webinar coming up soon, where we talk about some of these other things, the risk and the testing and reuse and metrics, dashboards, and that kind of thing. But that's going to be for another one, because 1 hour is not a long time for the material that we have. So I'm going to switch over here, Eva. Let me do that.
Well, Warren, if it's okay with you, while you're switching tools, I wanted to do just a quick unofficial poll of our attendees.
Yeah, that'd be great.
I have a question for you guys. What SysML diagrams do you use the most? And you can use the chat feature in your control panel to type in your answers. All right, we've got some answers coming in. We got Arthur says sequence diagrams, Bill requirements, Stephen state transition diagrams, Laura says she uses sequence diagrams, Ian says activity and state transition diagrams.
All of them. That's good. All right. Well, I'll touch on all of those then in the time that we have.
Oh, here David says block definition diagrams. Keith says I have used BDD and IBDs the most.
Some architecture people in the audience today. That's what that tells me. Okay. Well, that's good. That's very helpful. I forgot that I should have shown this. Today we're going to demonstrate on a medical device example. It's a breathing machine called a ventilator. We call it the quote-unquote Vitek ventilator. It's an example that we pulled together last May and June for our Genesis and Core webinars. So that's what you're going to be looking at. Okay, well, that's good. So let's go ahead and dive into it. We'll do this for about 20 minutes or so, and then we'll take a few questions afterwards. So when you first come into Core, what you're going to see is a particular project window. And so I'm going to go ahead and open this project for this webinar. And the way Core works is that we have several elements to the tool. The first one is an explorer view of the tool, and it includes some project properties. It includes a lot of information representing those domains, like the architecture domain, components, behaviors, functions, and states. We have a list of requirements, and these numbers represent how many of those things are located inside the folder. And you can see we have use cases. We also have lots of test information, which we've decided to save for the next webinar. There's also some information down here in the utilities area. There's a great notification center, so when you're working collaboratively with a large team, you can actually subscribe to different portions of the model, and Core will tell you when someone has touched a piece of the model that you're interested in, and you can go and see if what they did affects your work. Now let's go ahead and go into the use case area. When I click on a particular folder, a list of all the elements that are in that folder appear in this pane here. So this is a list of all the elements, and you can have subfolders. Up here I can show you there's a subfolder. But if I click on any one of these, like I just did, you're going to see some information about this element. So remember, we're kind of a database-centric tool, so that means that this is a use case of the system, this ventilator system as whole, and it has a number of different system attributes associated with it. You can see the primary flow, precondition, post-conditions, the alternate flows. And you can just simply type information in to the tool. You can adjust fonts. You can do different kinds of things and make it italicized and underlined and whatever you'd like. Down here, we're not going to talk much about this, but I do want to point out that down here we have a set of all the relationships. Remember, I made a point twice now about the diagnostics capability. We have a diagnostics tab, and those relationships help the tool identify the gaps or those missing jigsaw pieces. I'm going to go ahead and I'm just going to shrink that down for now. We'll be talking about relationships more later. So when you look at this particular use case, you can see that the ventilator is intended to be used by children in hospital settings. It will be operated by nurses or other hospital staff, and will be maintained by various maintenance personnel. So that's kind of a high-level description. There's more information in there as well, but that satisfies for now. We have some preconditions with the use case. There's co-locate, there's power, and so forth. Now here's the primary flow. I've highlighted a couple of things, a technique that when I taught this many years ago at the University of California Extension, I would tell people to highlight the nouns, and they are potential components in your architecture, actors. Highlight the verbs, those are potential behaviors or system or functions of the system. And so in this case, I've highlighted 4 different things that the system must do to represent, in this case, some of the subordinate use cases that the system must do. It has to be initialized. We have to set it up to help breathe for a particular patient, a child in this case. It has its basic respiration and monitoring functions, its operational state, and then of course has to be maintained and calibrated as well. So here we have a nice textual use case, and I'll show you how this can be printed out. But down here at the bottom of core, we have a number of tabs. So I'm going to click on the use case tab, and you can see that I've already gotten started with this use case. I've identified the second one of those, the patient setup. But let's go ahead and build a use case model associated with those 4 elements. So for instance, we have to have a use case to initiate the system or start up the system. So initiate the ventilator. We're going to have a use case to simply operate it or breathe for the patient. This is the basic operation of the system, and then we have maintenance. We need to be able to maintain the system. So okay, so what about the actors? Well, the nurse is going to do the patient setup and turn the thing on. So we'll put a new actor on here. Feeling went down here. Make that the nurse. And the nurse is a person, so I'll go ahead and identify this as a human. An actor is a component in core, so it can be an external system, it can be a piece of software, a piece of hardware, whatever you might need. In this case, we're going to make it a human, and it'll become the stick figure. And we'll hook that up to these guys. Okay. We'll have a maintainer as well, so we'll go ahead and put a maintainer on here. And hook that up as well. Okay. The patient will be the actor with the breath, so we'll go ahead and put the patient on there. And now we've got our actors all hooked up. Okay, so one of the maintenance functions associated with the ventilator is to calibrate it. So if we want to give a patient a certain amount of pressure, pounds per square inch in each breath, we want to make sure that the machine is calibrated so that it doesn't give too much or too little. So we can do that easily with our generalization. We'll create a calibration calibrate the system, and that goes in there. If we wanted to put some text in here for calibration or any of these, we can do that just right here. We can open it up. You can see that we've added that, but I can just come over here into my text area and find calibrate, and I can put the description right here. I can identify what the preconditions are, and the post conditions and so forth. And all that information goes straight into the definition of this calibrate or any of the other use cases. I can hide this. If I open this calibrate use case up, you'll see that the text that I just put in is actually there. We can do the basic includes and extends. Includes, like for instance here with patient setup, we may need to enter the patient data. This is a task that would be reused over and over again, a use case that might be used elsewhere. So by making it an include, we can use the same use case elsewhere in our system designs where we would need to enter patient data. We can also perform exceptions. So for instance here, if the system's operating and breathing for a patient, this is a hospital ventilator, we might sell it to countries that maybe don't have the most secure power system. So I can click on the little extension button and add an extension or an exception, if you will, that says that there's a power outage, what we'll do, and make that an extension. You can identify the condition. So you can type in the condition. So the power goes out because of a blackout, and that gets represented there. You can also represent those, of course, using the other notation. So there's a lot of richness in this capability to specify your system using SysML here in Core. Okay, so let me go ahead and show you, take you to the next step. We've done some systems modeling now, and we might want to derive some requirements from this. I happen to have pre-filled this patient setup, so I'm going to go ahead and open that up. And you can see that the primary flow of the patient setup, this is actually hooking the patient up to the ventilator with the tubes and so forth. You can see that the primary steps that the nurse needs to take are to view, to get an indicator from the ventilator. The machine will say, okay, go ahead and hook him up to the tubes. The nurse would intubate the patient by inserting the tubes and notify the ventilator, okay, I'm done, then add some information in and start ventilation. So this is the primary, these are the steps that we've identified in the use case. What are the requirements associated with that? Well, one of the things that's really great about Core is that you can do all your relationships using drag and drop, just like I did over here with the drawing. So I'm going to come over here and I'm going to identify my requirements. Now I took the initiative here to pre-write some requirements, so you can see here that I have some requirements written that kind of correspond to those steps. You obviously have to do that, but they're not linked up to anything. So I'm going to go ahead and do some traceability. I'm going to select these requirements, oops, and I'm going to drag and drop them on, and you can see that I get a dialog box. So this requirement, is it what's the relationship to this use case? Is it listed by the use case, or is it the basis of the use case? We might have requirements and we do use cases from them. In this case, we did the use cases first. So let me go ahead, and I did the one. I'll go ahead and do the rest of them as well. Okay. So now I've got 5 requirements allocated, or derived rather, from this use case. So let's go ahead and move over to the requirements. and take a look at them. Here are those requirements. I've gone into the requirements field here, and I'm going to go ahead and start looking at them. Now these requirements are all under the setup area, so I'm going to go ahead and look at this. If you see down here, we have some tabs along the bottom. These are view tabs. So I'm going to click on the requirements view, and I can actually see all these 5 requirements associated with that just associated with the use case. And you can see the system shall provide an indicator to nurse. This is the one that I just showed you. And I can start linking these requirements up to my system design. Okay? So I actually have defined some functions associated with this. So I'm going to go ahead and link those functions up. If I hadn't defined them already, I would be able to create new ones, but I'm going to go ahead and hook the second requirement up to the second function, and you can see it gets added in there. I can do the same thing for the third one. And I'll slide over and do the same thing for the fourth. Now, one of the things that's interesting about core, remember I've mentioned 3 times now about the diagnostics capability. What exactly does that mean? Well, as you're doing your system design, you're doing SysML, but what's the model providing? Well, the model is keeping track of your work. It's telling you whether or not you have a complete system design. So if I open up, for instance, this requirement here in its own window, I have these tabs down here. I can click on Diagnostics, and it will tell me if I have any errors associated with it. This one doesn't look like it has any omissions, any design omissions. Let's see if another one does. This one is good too. I'll pick one more here. Oh, they're all good. So, so that's nice. But what's really cool is that by using the diagnostics capability, I'm able to identify any system design omissions that I might want to do. So moving forward, I'm going to add one more piece here. I'm going to create a test procedure associated with this requirement. So I'm going to drag the new verification requirement on here, and I could, when I do this bucket, I could now build a test method associated with this. So I'll go ahead and open that up, and I'll just put that's method 1. Okay. So by using drag and drop and the capabilities of the tool, we can start to build these models. Now let's go ahead and look at the activity diagram that is used to represent and implement these different requirements. These tasks correspond to that. So I've actually gone and built an activity diagram associated with this. You can see that we have both an activity and sequence diagram over here. I'm going to click on this tab, and I've opened up an activity diagram. So this represents that primary flow from the use case. Remember, the primary flow of the use case was the system aiding the nurse in setting the patient up. So here we have an example of the function to notify the nurse to intubate the patient, and we have a representation of what the display would show. Here we have this flows in the activity diagram over to the next piece, which would be the system supporting the nurse and intubating the patient, maybe by providing clean tubes and sterilized tubes, that kind of thing. There would be a control for ensuring that the intubation is complete, that the nurse would hit so the system knew. Then they would go through a system a stage where they would enter the age and weight and ID of the patient, and then press the start button. Now I've put graphics behind this because it's very easy to represent this to your end users and so forth if you do that. But you can either have those on or not. Here's what it would look like with the standard uh, SysML activity notation. You can see that there's some decomposition here by this indicator, and I can either put that image on or not. So I'll go ahead and use the image again. I can drag and drop and build this up and so forth. I'll show you that in a minute. But as I mentioned, this guy here actually is decomposed. Let's go ahead and look at the detailed behavior that the system is performing to enter this patient data. So by opening this up, I have essentially, I'm looking inside this guy. And what we can see is that there's a more activity diagram. There's a series of activities that are being performed by the nurse in this case. That's this swim lane. And here by the control system of the ventilator. They control the interactions between this thing. So the nurse will, the system will request that they start the authentication of the patient. So the nurse will enter, that's on the display, the nurse will enter the patient's information, maybe scan an ID card or enter in their name and date of birth. In this high-tech device, there will be a photo that's offered back to the nurse of the patient, so the nurse can compare the photo to the patient, say, oh yes, yes, I authenticate and acknowledge this is the patient, and then it goes on and so forth. So as we've built these artifacts, they've been populating the underlying model. So if I wanted to, say, add a new node to this, I'll just call it function 1, I can do that in this view, and it will go in the model. I can also do it in any other view. And in fact, if I bring up another view, I'll bring up the, there's a lot of interactions here, I'll bring up the sequence diagram view. So this function 1 I just created. Here's the sequence diagram view. It shows the exact same processes or functions. It shows the same interactions, and it shows the lifelines, what the architectural component is of each of these. And what about function 1? Well, I just added function 1 to it. There it is. So I can edit in the activity diagram or the use case diagram or any of the diagrams, and it populates the underlying model. And then it will reproject that on any other picture. So, for instance, one of the things that's nice about this is that by doing that functional decomposition, Core gives me a functional hierarchy if I want it. It's one of the tabs. I didn't have to do any extra work to get it. And I can edit here as well. I'll make it simple. I'll just take that off. You see the unallocated lifeline went away, and when I go back, now function 1 is gone. So you can edit from any of the diagrams. Okay, so looking at this, where does this this activity diagram, this process flow live? Well, this actually lives inside of a state model. Okay, so I'm going to go ahead and bring up the state model. So I've gone into the state area. I've brought up the state model, and you can see we can draw and so forth. I'll do that in a second here. And you can see that we have the system is initiated. When the control system is powered up, then the control system will initialize the controls and displays. The control system will also initialize the pump, which is the respirator. When that's done, then we will go into the ventilator operations, the breathe and monitor. Patient setup, this is the one that we just saw. So where does this live? Well, if I open this up and look at those relationships, you can see patient setup, and boom, here's the diagram that I just showed you. So what does this mean? This means that you can control which states your behavior will exhibit in. And this is a very innovative way of modeling this. What we've done is we've blended the more traditional functional perspective with the object-oriented state perspective. So it's easy. We're running low on time. You can certainly do all your editing that you want as well. And you can add transitions and events and so forth. You can have Pardon me. You can have transition activities that occur when you transition, and I won't spend any more time on that, but it's very easy to create these diagrams. And this little indicator here means that this state is decomposable. So here's the substates that live within this state here. Okay, so I'm almost done. I want to show you, I guess the last piece really is the component, the architecture piece. We have some architects out there. So we have the component area where you capture your interfaces and components, and there's a lot of richness to both. I'll go ahead and open this up using the structure block definition diagram. You can see that we support that, obviously, and we also support the generalization diagrams as well, and that information is all captured in there. One of my favorites is the flow block definition diagram. So I'll go ahead and click on that, and you can see, in fact, this might be a better one. You can see all the links, physical links, and all the data that's goes across those links. Now, in the last couple minutes, I'd like to show you two things. One is I've been talking about traceability. You can get very nice traceability diagrams out. We have a great trace tool that will export that for you in a variety of formats. So I've got one set up here for the webinar, and we'll just output it here. So what Core's been doing is it's been keeping track of the work as I've been building these relationships between use cases and requirements and so forth. So here's a list of the use cases. So this use case elicits these requirements. So here's a requirement that elicits. Here's another one. All those 5. This is the requirements text. It's implemented by this function. This one is implemented by this function. Here's a description of the function. Some of these are allocated to components. Some are not. You can see that it's giving me a gap analysis. Some of these are allocated, like patient setup, to a state. So I can see that this patient setup is exhibited in the ventilator operation state. Finally, I have one test that verifies this. So one of the things that's really awesome about Core is that it can give you this gap analysis. It's like the missing pieces in the puzzle. And in fact, we have an entire report that will give you all of the gaps for the entire diagnostic results report for the entire system. So I'm going to do it for the entire project. And where I showed you the tab of the so I could look at gaps on any individual element. Well, here I just got a 12-page report showing me all the design omissions on every element in my design, the architecture, sensors, the functions, the behaviors, everything in one report. So think about this for a second. What I've just shown you is a way to do your modeling, your SysML, in an underlying MBSE repository, and then have the tool tell you all your design omissions. If you clear this out before you get to integration and test, you will avoid hundreds of defects in your system design. The last aspect of the tool is documentation. We have some great documentation generators that where you generate the documents straight from Core. I'll go ahead and run one. It will give me a table of contents, and you put your logo on it, the whole 9 yards. I'm choosing only the SysML artifacts, and here it is generating from the model all of the pieces of the document that I might need. It's including all the interfaces. It's including all the a glossary, header. I can identify our company's name, we put our logo on it, so forth. And what you'll see here, I'll go ahead and there's a lot of pages of requirements, originating requirements that were in there already. I'll go ahead and come down to here are some of those requirements that we looked at during the webinar, the statement of the requirement and so forth, what it's linked to. I'll just keep moving on. Capturing risk information, which we'll be talking about more in the future. That was also in the model. Here is the use case. Here's the Vitek ventilator use case. You recognize these red areas. Here's the diagram that I generated. It output just fine. And then these other pieces, the patient setup and so forth. And so when you come through, you'll see all of your functions, all of your views, your diagrams, the whole 9 yards. Interfaces, all defined. You can do it for any one piece so that you can give it to a supplier and say, well, here's the behavior interfaces you have to meet. It'll give you an item dictionary. And at the end, it'll even give you an acronym list and a glossary automatically. So, Eva, I'm a little bit late here on time. I thought that I would go a little bit faster, but that's what I had prepared for today.
Oh, that's quite all right. I don't think anyone minds. It was really interesting. So, real quick, we have quite a bit of questions. Let's see. Our first one is, I know this is something you're very passionate about, so Stephen wants to know, he says, I always thought SysML was MBSE. Why do you say they are different?
Well, I went to the INCOSE International Workshop almost a year ago now, and sat in on some amazing presentations in the MBSE working group. And what I noticed was that a lot of people assume that if you're making a diagram using SysML or some other notation, you are making a model. And what I contend is it's kind of like an architect. An architect can draw a house, an elevation view, a plan view from the top, a side view. He can make 3 drawings. He doesn't have a model. A model is what you make out of balsa wood that you can walk around. And it's kind of the same thing. The SysML is awesome. I love SysML. It's a great notation. It's very helpful. It's a great communication tool. But a diagram is a view. The model is, as I've shown, how is the information that that view populates in an underlying repository of some sort. Thanks, Stephen, for that.
All right. Our next one is from Keith, and I know you touched on this during your presentation, but I think he wanted a little bit more detail, and I think others wouldn't mind either. He says, I continue to be confused with the activity diagram and the sequence diagram. Please provide further information regarding their differences when you use one versus the other.
Well, that's a good question too. When I came to Vitek, I was not clued into the possibilities of having the model generate 2 different views, a sequence diagram view and an activity model view from the same underlying data. So now that I work here with Core in Genesis, I'm able to have both. So that's the first thing. But to answer your question very specifically, I've done a lot of modeling using SysML, and I used activity diagrams when I was representing a series of loosely allocated activities in a time-phased fashion for presentation to a customer. So if the customer said, I want my system to do X, I would model X using activity diagrams. Then I would use sequence diagrams, since they're very narrowly tied to the architecture. Each lifeline is an architectural component. I would redo each piece of the activity diagram in a sequence diagram to show the specific architecture and negotiate at that architecture with the different team members and groups inside our organization that need to implement something. So then we would negotiate the interfaces between my component and your component, or his component and her component, that kind of thing. Now that I'm with Vitech, I actually use the activity diagram more than I did. I used to use the sequence diagram exclusively for that. Now I use the activity diagram more because I can add both swim lane information, like the nurse swim lane, and I can add component information on each process or activity. So hopefully that helps. And I'll be glad to talk about it with you more if you'd like.
All right, thanks for that. Next, we have a question from Lori. She asks, how do you open the parametric diagram in Core?
Core does not have a parametric diagram. We do manage parameters in along with all the other elements. So we have taken a different approach. We have parameters associated with requirements, tests, functions, and so forth. You can define your own, and so forth. We have been talking about adding a specific parametric diagram into a future release of the tool.
All right. Next up, we have a question from Fatma. Do you validate on the SysML spec or just completeness of the model?
We validate completeness of the model. Yes.
All right, short and sweet.
Mm-hmm.
Michael wants to know, he says, although not a part of SysML, we are currently using IDEF0 models for our functional architecture. Is there a capability to simulate IDEF0 models in Core to demonstrate that the functions work together to meet the operational requirements or concept of operations?
Yes, there are. So for people that aren't familiar with IDEF0, I mentioned that systems engineering has been performed for many, many years. And IDEF0, functional flows, and some other n-squared charts have been around long before SysML. We support all of those inside of Core, so you can build a model or a diagram in SysML, and then flick over and view it in IDEF0. And yes, you can actually simulate, if you have the temporal information in there somewhere, a functional flow or whatever, it will in fact simulate an IDEF0 and follow all of the different threads through your I/O. One of the things that's nice about Core is that if you have some people working in the SysML domain, and you have others that want to take out that temporal information and just view the static functions and what their interactions are, you just click on the tab and there it is. It keeps them all in sync and everything. It's awesome. It's really awesome.
All right, thanks, Warren. I have another question from Fatma, and I apologize if I'm butchering your name. She says, is this sequence diagram generated automatically from the activity model, or did you do that offline before the webinar?
No, it was generated automatically. And that's why I wanted to demonstrate that by adding that function 1 and then showing that it was automatically placed on the sequence diagram in the unallocated bucket. If I had allocated it by, say, dragging and dropping the display component onto that function 1, it would have moved over to the right swim lane, the right lifeline. So yeah, the thing that's really nice is that with Core, you don't have to make every diagram by hand. You build the diagrams you want, and then it will project out for you the rest of them. And all those diagrams, like you saw, are available for the documentation. You can just print them out in JPEGs or PNGs, whatever you'd like. It's an unusual concept. It's not one that people are really necessarily used to. It takes the same amount of time in Core, maybe a little bit faster, but it takes about the same amount of time to draw a diagram in Core as any other tool. But then you don't have to draw a whole bunch of other stuff because it gives it to you for free. You want a spider diagram? There it is. You want an IDEF diagram? There it is. You want a hierarchy diagram? There it is. It does that for you. And it keeps them all in sync because they're all being projected from the model. Okay, I'll stop talking on that one. Any
Okay.
others?
I was wondering when to jump in. I have a question from Hongman, and I apologize again if I'm butchering your name. He asks, what types of API are available in core to access SysML model information programmatically?
Yeah, we do have an API in core, and it's documented. We have an API reference manual. Um, Honestly, I'm not that familiar with the API. We also have a companion product called Genesis. It's a less mature product, but it does the same types of things that you've seen here today. Genesis is actually got a a more robust API. It's a Visual Basic API. Genesis is built on a SQL Server um, basis on a database. So you know, it's there's certain customers that Genesis will work well for, and then Core has many more features, obviously, and has been around much longer. So we have more customers that are on Core because they just need that added feature set. But both of them have their respective APIs.
All right, a couple more questions if that's okay with you, Warren.
Sure.
All right, Joseph asks, are you able to produce a class diagram?
Mm-hmm. Yeah, in fact, I just showed you one element, but yeah, the class diagram generates just exactly like the other diagrams I showed you with the hierarchy, the inheritance hierarchies, and so forth.
All right, I have a question from Lori. How do you show the stereotypes on relationships like those on the requirement diagram?
Um, the stereotypes typically are based on the relationship type. So in many other tools that are kind of diagram centric, you actually have to go in and label each stereotype. But for instance, in core, if you relate a requirement to a function, it will automatically stereotype that relationship as this with the satisfies relation stereotype. Or if you relate a requirement to a test, it will give it the verifies stereotype. And that was a slide that I accidentally left out. But and then if it's something that you would specify, there's a relationship attribute that you can set.
All right. One last question. I know we've gone a little bit over, and I apologize for that, but we've had so many great questions. I just hated
Good.
to not answer them
Yeah, I'm sorry to keep
live.
people past their lunch hour.
Yeah,
I guess it's lunch hour for me, but not for the East Coast. Okay,
that's right.
what do you have? What do you have?
I have one more from Hongman. He
Okay.
says, does core provide capabilities to simulate or execute SysML diagrams or solve parametric diagrams?
It does have simulation capabilities. Um, so that will be in the next webinar, our simulation capabilities, and SysML activity sequence diagrams can be simulated, and you can assign functional durations. You can link it to architecture. So for instance, if you have a narrow data pipe between two architectural components, that will be reflected in extending out the simulation time. You can identify resource constraints, um, and the tool will, when you do your simulation, which is really it's a virtual prototype of the system. You can see how the system will perform right before your eyes. It's really cool. Just not enough time to get to it today. And you can do that from SysML diagrams. From parametrics, we can program in using some scripting the relationships between parametrics using the parameter classes, the parameter capability that I mentioned earlier. So that does require some knowledge of our core scripting language. But you can do simple things like roll-ups and that kind of thing just out of the box. We have customers, like a lot of our space customers will have weight budgets and actual weights, and they'll just do the roll-ups of those parameters with the out-of-the-box features.
All right. Well, that wraps up the Q&A for today. I apologize if we didn't get to your question, And we will contact you directly to ensure that it was answered. And if you think of any other questions or comments that you didn't get a chance to send in, we invite you to post those on the forum of our community site, which can be found at community.viteccorp.com. And let me give you the link to that. All right, there it is. And as I mentioned before, a recording of today's webinar will be posted in the resources section of our website within 24 hours. So that just about wraps up today's presentation. I thank you all for joining us, and I hope you join us next week for Systems Engineering in Turbulent Times, which is being presented by our very own president of Vitec, David Long. And let me chat out that link to you so you can register directly. Also, at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on any topics you'd like to see covered in the future. We have added some new questions to help us determine the best time to hold our live webinars, so please let us know what works best for you. So that is all for today. Once again, thank you very much for joining us and have a great day.
Thank you, everyone. Thank you, Eva.